Hey, question.
I was looking into the Cantor set this weekend. I was having trouble describing the position of each of the points. Do you have to use a ternary representation to do that?
Which representation is this? What representation is
It's
this?
ternary, like the ternary number system where you represent it in like 0, 2, and 1. It's basically like a modulus kind of representation.
Probably not. I don't know though.
Because it's not just the endpoints, because like 1/4 is never an endpoint, but it's also in the Cantor set.
That's correct.
So you can't define it by just the endpoints themselves.
Yeah.
And I couldn't find your paper that you had mentioned that was on fractals. I saw one about it mentioned the Sierpinski triangle, I think. Was that the paper that you were mentioning?
Does it not have it?
I checked on the SFIX or the SPHYS website, and it says your publications on archive.
Yeah.
I looked through them. I just saw one that said Sierpinski.
Yeah, that's
the one.
There are only 2 papers on fractal actually. One is that, and let me think. Which one did I have? Yes, it is the previous one. Actually, it is called self-similar configurations. I think Casimir energy of self-similar configuration.
I do think I saw that one actually.
Yeah, so there are only 2 on that. So I can quickly search here, right? Wouldn't. Yeah, it is this one. 16700214. Yeah, maybe that's not sufficient, but still, I'll look into it. Now that you asked me, maybe that's not obvious.
Yeah.
How to put in that. How to define the setups.
And I was looking, there wasn't really like a simple, like standard representation of the Cantor set itself.
Yeah,
That's all in like the ternary.
Let's see. Yeah, this is what I do. Yeah, I don't use delta functions. Yeah, I don't define any such thing. Maybe it is not easy. Yeah, let's think about it.
Yeah, I didn't spend a crazy amount of time on it. I kept getting stuck with the same thing, so I kind of gave up on it. Department of Physics homepage. Is that what
Yeah, but do that again? Oh, yeah. Yeah, that's correct. Yeah. I thought for a change you were saying, did the Department of Physics page come up? My page on the department is not yet.
But it is making its way back, at least.
Yes. Broadly it is there, but the individual pages are not there. Anything that was residing on the server in the department, that's gone. They have not yet fixed it. They took the computer and then I don't know what they're doing. Okay. Matt and Curtis. 3 minutes, I think I can. Riley and Travis. 2 + 2 missing. So Matt and Curtis, you guys got disconnected last time.
Yeah, we did.
Yeah.
About 10 minutes left.
10 minutes left. Yeah, I did actually go back and look into the video as to where we really got off. But I'll start from a certain point and let me know if it is completely off or not. Okay. So.
Okay.
What happened was campus-wide Wi-Fi shutdown.
Okay. Did you get an email or something about it?
Oh, there were other people talking about it.
I see.
In my phone.
You're down. Okay. So it was not just video. Because for a moment I thought it was this room because in the morning, 11 o'clock, it took a little, I would say, double the time that usually takes to log in. It kept circling and I thought, oh, is it this room that has a problem? But it is, then it went fine. So I'm sure there was a university outage. Okay. Isn't there a homework due today? I guess you guys submitted and I haven't looked into it yet. So there's a next homework is homework 3. No, homework 3 is not due, right? But it's relevant. Homework 4 is due on Friday. And notice that September 7, on which we have a class, that's a Monday, that's a holiday. So we miss a class, and homework 5 will be due September 11, which is Friday, and we will have the midterm on the same day. I try not to keep the exams on the same day as the exams, so be responsible about it. You won't get things graded. That's our understanding, unless you submit it way in advance, like at least 24 hours in advance, then I might grade it. But otherwise, you don't get graded. So be responsible about whatever you're doing. It is about Gauss's law, what I will be doing in the last week. So I think it is very much, most of it, you have already done it in the introductory level. So most of what we're doing is kind of collecting stuff from everywhere else. At least you should have some, you should feel that you've seen this in some form or the other before.
Is homework 5 going to be on the midterm?
Yes. In fact, that will surely be there because this is on Gauss's law. So this will be the first thing of electromagnetism we will see. This is on delta function, right, that we'll be working on. So at least expect one problem from each homework, including homework 3. Right, so that's a very easy thing for me to do, that pick or design one question on each homework. And give some extra, like Gauss's law, I will challenge a little. Rest of it, I will just make sure that you have understood the concept. But Gauss's law is where I might challenge different from the homework problems that I've asked or something with that. So be prepared on that. Any comments or questions on that? Matt and Curtis?
No questions.
Thanks. Okay. So let me do whatever we were doing, or at least today's lecture should give you enough introduction for the homework. You should be able to do all the homework for this week using whatever I'm doing today. Delta function, we studied it as a concept last week in the last lecture. Today, what we want to see is just its usage, and that's how we will see it all through in the semester. So delta function as a user level, not at a concept level. At a concept level, it is that it is if you have a function defined, so at a certain point it goes to infinity, but it goes to infinity in such a way that if I were to integrate about this point anywhere, it gives you 1. That means that infinity has to be inverse of the distance. So delta function satisfies this identity that this is equal to 1. You can say this is minus infinity to plus infinity, but it is also true that you have, let's say, how should I say? So this is a to b dx. Delta of x is equal to 1 if a is less than x and b is greater than xl, not x 0. Okay, so that's our basic idea of a delta function. So immediately we extend this to say if a to b x, or maybe I should also add a feature to this, that this is also equal to 0 otherwise. That means to say that if this doesn't belong to that set, that means 0 is not less, or if both a and b are on one side of 0 and a and b are on the other side, then it is 0. I can always multiply a function. I think this is what we were doing at the end of a lecture last time. Notice this is a sum of a lot of quantities. Integral should be thought of as a sum, but delta function is 0 almost at every point except at x equal to 0. So if I remove that, since it doesn't, it is equal to 0 everywhere, I just have to talk about f of 0 times minus infinity to plus infinity dx delta of x. Right? That's one way of writing it, because it is valid only at one point. Right? I can remove it, and rest of it is equal to 1. So this is equal to f of 0. Again, what do we mean by this is that if you have a delta function multiplied by f of x, it gives you f of 0. That's the way we want to use it. Okay. So that's our identity here, that any function multiplied by delta function integrated, you get f of 0. Oops, this is a to b. I can generalize this in a simple way, and whenever I write minus infinity to plus infinity from this point on, it is understood that it also is satisfied for any set in between. So I'll keep writing minus infinity to plus infinity. So this is minus infinity to plus infinity dx. The delta x need not be evaluated at x equal to 0 or survive at x equal to 0. It could be at an arbitrary different point. So it's x minus a times f of x will be equal to f of a. So that's our simple identity, that function multiplied by delta function evaluates at just one point, right? It survives on that. Now we want to extend this further. We want to do this slightly differently, right? This is any linear function. What if there is a constant multiplied by that? So this need not be always x minus a. So this is b of x minus a times f of x. And we would like to know what that is equal to. Right? What could this function be in? So the only difference here is that b is multiplying this x, and we would like to know what that is. Since delta function is pretty much 0 everywhere, we should ask at what point does this survive? Right. So, what are the guesses? Any guesses here? What it might be? It seems like whenever this is 0, that's when it survives. So here it should be b of x is equal to a, so it's x equal to a over b. Right? So this seems to be saying that this should be f of a over b. But it's not very obvious that is that all? Is there something that it gains from here? Is there a coefficient here or something like that? So it's not very obvious. Right? Maybe this seems to be what it is. So let's put a question mark here. Like, is there a coefficient it comes up with? Is there a scale? How do we know the scale? Like, especially when this is infinite at that point. How do we know what's the difference between delta of x minus a and delta of b times x minus a? So we want to do this a little more concretely. So let's call this I. Let's call this I and evaluate this in a little more algebraic way. So to evaluate this function I, so let's make a substitution. Let's substitute y is equal to bx minus a. So I'm interested in evaluating this integral. So I make a substitution of bx minus a. I have a dx showing up, so I would like to convert that to dy. So that's b times dx. So if I'm evaluating the integral, I have to worry about its limits, and dx is nothing but dy over b. Delta of dx minus a is nothing but delta of y. And f of x is nothing but x has to be written in terms of y. So I would say it is y plus a over b. And I have to evaluate the limits. So let's ask the question. When x is equal to minus infinity, what is y? And when x is equal to plus infinity, what is y? And we immediately realize that there is a catch in here. It might seem like when x is equal to minus infinity, y is equal to plus infinity. But that's only if b was a positive one. If b was negative, it can flip. Correct? Notice how it goes. If x was, this is equal to minus infinity if b is greater than 0. This is equal to plus infinity if b is less than 0. Is that clear? What I mean? I substitute here x equal to minus infinity, or in that approach, in that limit, but it depends on whether b is plus or minus. And the same thing here, this could be plus infinity if x is equal to plus infinity. This is so if b was greater than 0, and it's equal to minus infinity if b is less than 0. There are two possibilities in there, and so let's worry about b greater than 0 first. We'll repeat it for b less than 0. So if b was greater than 0, this is indeed minus infinity to plus infinity. And once I have this, what is this equal to? So this is what is this function evaluate to? Notice now I have something like this. Or, yeah, this one, right? What does this evaluate to? F of a over b over b. So my prescription is that set y equal to 0 in the function, and there is a coefficient in front, so it's 1 over b. So it's a over b. If b was greater than 0. Is that clear? Any questions? This is what we will again and again use. If you ever see a delta function inside an integral, That's the easiest integral we can do. You look for the function, anything that has a y dependence in it, set y equal to 0. Or in this case, it is y equal to 0. If this was any y minus a, then you set y equal to a. Is that clear? Any questions on that? Travis, Curtis, Matt?
No, we're good. I'm good.
Yeah, so we'll keep repeating this, and this is what your homework is also about. Make sure that you also look into the limits. You want to make sure that you use the fact that if you're within the limits, it is 1, otherwise it is 0. Right? You also want to make sure you use that fact. Again, if I were to repeat this for b less than 0, the only difference is that the limits change, rest everything remains the same. So this is plus infinity to minus infinity, dy over b, of y, f of y plus a over b. Again, delta function is evaluated the same way, but now you want to change the limits before it works, right? You want to change the limit that is equivalent to putting a minus sign, right? So that's minus of minus infinity to plus infinity. That's again for b less than 0. Now evaluate this using the idea of delta function. So it's minus 1 over b, f of a over b, if b was less than 0. So it seems to suggest that this is equal to 1 over b times f of a over b if b was greater than 0, and it is 1 over minus b f of a over b if b was less than 0. Notice b is intrinsically having the sign here. If b was greater than 0, it is the magnitude, of course. But if it was less than 0, minus b is nothing but the positive, so it's the magnitude that is coming up. So this can be compiled as magnitude of b times f of a over b. And that is what is the coefficient in there. So now we know it clearly that this is equal to the coefficient times. Okay. So some examples immediately. So I can do, let's say, a 1 to 3 d of x times delta of x times, let's say, let's keep our function always the same. About yeah, just randomly some function 3x squared plus 2x plus 1. Right. What is this equal to? It's equal to 0. Very good. Like, I don't even have to evaluate, do no work. First, look at the limits. Here, this survives when x is equal to 0. That's not within the limits. Don't even worry about anything. It's a 0. Nothing at all. Instead, if I had done minus 3 to plus 3 dx, same function here, so 3x squared plus 2x plus 1 Hello?
We're back.
Yeah. Okay. How long did you lose us?
30 seconds, maybe a minute.
Okay. Yeah, I don't know what's happening. Not in my hands, so we didn't purposefully.
It's all right. We'll figure it out. We'll be good.
Yeah. Okay. So you guys are there until this example, second one?
Yeah, I think I finished I wrote down the first one and then we disconnected, so we're not too far behind.
Okay. So what we were doing is that okay, we did this example. Here it is 0 because this survives at x equal to 0, but that is 0 is not within 1 and 3. Right? So you immediately say that's 0. Okay, so maybe write the reasoning here because 0 is not between 1 and 3. And why is 0 so important? Because it is x equal to 0. Right? You set the argument equal to 0. Right? That is how it survives. In the second example, again x is equal to 0, but now it is within the limits, -3 and +3. So it does survive. So you set 3x squared plus 2x plus 1, and you set that at x equal to 0. And you evaluate that at x equal to 0, that's equal to 1. The third example is the same one, but now when I set x minus 1 equal to 0, it is x equal to 1 that survives. So I will evaluate this at x equal to 1. And that, as some of you guys told me, so I evaluate this, so that's equal to 6. Any questions on that?
No, loops is pretty straightforward.
So next example, -3 to +3 dx delta of, let's say, 2 of times x, not like 3 times, 3 times x minus 1. Okay. Be careful how you proceed on this. Yeah, let's have some answers. Yeah, can you guys?
Two-thirds.
2/3. Okay. What's addition is 2/3? I don't know the answer. I started doing it in my head. I'm not finding it. Okay, so let's evaluate this. Is it clear how to proceed, everyone? Or why don't you guys work and get your answers?
I got 2.
2. So there's a 2/3 as an answer. There's a 2 as an answer. What do you guys get? Matt, Curtis, and Faust? Let me know when you're done. You're going to wait. Okay.
I have 2/3 as well.
You got 2? Is that what you said?
2/3.
2/3. Okay. Yes. So I'll say 2 of them.
Yeah, same.
Same. Okay, so that seems like 2/3 might be the one. So let's see. So remember that I'll first do 1 over magnitude of b. So there's a 3 there. Right? So it is 1 over magnitude of 3. And then I have to evaluate this 3x squared plus 2x plus 1 at x equal to. That is not at 1, it is 1 over 3, right? This is a over b. So I have to evaluate this at x equal to 1 over 3. So that's the same as 1 over 3 times 3 over 9 plus 2 over 3 plus 1. Right? So what is this? 1 over 3. So it's, yeah, this is 1 over 3 plus 2 over 3. That's 1 plus 1, 2. That's 2 over 3. So probably those who got 2, you miss the factor of the division of 3. And that probably. That's the main idea of the delta function. Now that is so. Here is what I can. Yeah. I think what's the homework? Should I be making it more careful? Homework. Computer. Yeah, I don't do anything of the next order. Yeah, so you should be able to do all the homework at this point, at least the first and second problem. And the third problem we'll talk about. Okay, so let me do another how we use this in the course. So let me go back. So notice that in all we studied, let's see the camera. Yeah, in most of the descriptions we studied in introductory physics courses, we typically talk about point masses, point charges, and so on. Like in this course, we talk about point charges. Sometimes it's a line charge and so on. So we would like to describe what is a point charge. Think of this as point mass, if you want. And what do we mean by point charge? It exists at only one point and nowhere else. So let's think of this as a point charge, position of the point charge. Position is typically a vector, right? So this is R naught, that's equal to X naught in the I direction plus Y naught in the J direction plus Z naught in the K direction. So out of all possible points in space, we specify that it sits at X equal to X naught. So that's what it means. Position is at coordinate X equal to X naught, at coordinate Y equal to Y naught, and at coordinate Z equal to Z naught. Which is the same as saying X minus X naught is 0, Y minus Y naught is 0, and Z minus Z naught is equal to 0. Right? That's a description we want to have. Immediately, we would like to ask, how do we describe this? How do we describe the charge of this? Instead of the charge, we will talk about charge density. So charge density of a point charge at R naught would be so this charge density means at every position of the space, what is the charge density? So this is equal to charge per unit volume. it should be equal to 0 wherever the charge is not there. So everywhere it doesn't exist, it is equal to 0, right? And at the place where it exists, apparently we don't know how to define that, right? So at least we can say this is equal to 0 if R is not equal to R naught. Right? And then we have to say what is this equal to if R is equal to R naught. There are only two possibilities. Either you're talking about the charge density at R equal to R naught, or you're away from it. But whatever it is 0 outside, and it is something that is not equal to 0. But we also know that charge density, when you integrate over the whole volume, right, over the whole volume, that means all space, right, all volume, let's say. So all space, I should get all the charge that's contributed from this point charge. So this should give you total charge. And let's say that this is a charge density of a point charge Q. There's a specific charge on this, that's a point charge Q. So that should be equal to Q then. And we get a scenario very similar to what we had earlier, that you have a function which is 0 everywhere, but when you integrate over it, it is not 0. So that means this must be a delta function. So this suggests that, so we will require that the charge density for a point charge to be Q times 3 delta functions, because we have to choose for each point, right? It's a volume that has 3 lengths. So that's delta of x minus x naught, y minus y naught, and delta of z minus z naught. We can immediately check, almost an instantaneous check once we have the identities. Let us see that if this is indeed true. The charge density over all volume, all space, let's say, that's equal to minus infinity to plus infinity dx, minus infinity to plus infinity dy, minus infinity to plus infinity dz times q of delta of x minus x naught times delta of z minus z naught. Like immediately you should see that this is actually equal to q, but let me explicitly do this. Q is independent of the integral. There are 3 integrals here, x, y, and each of this integral is 1. There is a chance that there could have been an x inside these. So whenever you evaluate 1, you have to set x equal to x naught in other places. But in this case, it completely isolates. So this is equal to 1. These are 3 disjoint integrals if you want. One does not connect with the other. That's equal to charge q. We can immediately talk about, so that's a point charge. What about a line charge? By a line charge, I mean a cylinder of infinite, let's say a cylindrical wire of infinitely thin radius. Or a better way to say it is infinitely thin cylindrical wire, like infinitely small radius. It's a small radius. Let's also specify when it's a line charge, a cylindrical wire could be anywhere I want to. So let us say it is sitting on the z-axis. So it is on the z-axis. And I should also say on the z-axis infinitely long. Or infinitely long and infinitely thin. Right? So it's on the z-axis, infinitely long, infinitely thin. So you will picturize this as there is a z-axis there. That's your x and y-axis. That's your x-axis, y-axis, and that's your z-axis. And it is uniformly charged. Let's say so this is positively charged. Now let me ask, what is its charge density? So charge density, it is on the z-axis. So what are the coordinates of the z-axis? Z-axis is determined by x equal to 0 and y equal to 0. Right? So there has to be two delta functions. So one is x equal to 0, which I'll write as x minus 0, and y minus 0, which is the same as saying delta of x times delta of y. I don't have to write zeros. But what goes in here? What goes in the front? Like here in this case, this was charge, but here it is not very obvious what it should be. First of all, what is the charge on this infinitely long, infinitely thin rod? If I say it is total charge is Q on this, that's a statement I can make. But if it is uniformly distributed, then it must be infinite because the length of the cylinder is really long. So this must be long. But what is a well-defined quantity there is charge per unit length. So let's define what is called lambda, which is charge, total charge Q per unit length. Let's say it is uniformly distributed on the wire. Charge is very large because the total charge on the cylinder is infinite, length is infinite, but they are of the same kind, so they cancel out, so this can be fine. This is fine. And let's say that's lambda. How do we check this? Are we going to get the total charge to be Q? So let's integrate this again, right? So integrate, or actually let me leave this as an extra credit. Exercise that show that d cube x times rho of r, right? All space should give you Q, right? When I
After lambda, does it say finite?
yes, finite. Even though charge is infinite, length is infinite, the ratio comes out to be finite. Right? So a large number divided by a large number need not can have well-defined quantities. But if you integrate over all space, again you will get the charge Q. So that's one thing. Let's now also do one more. Feature. Let's define what is called a Heaviside step function. Right. And this will be defined as a function theta of x. Often you will use the letter theta for angle, but this is also for step function, but usually in the context it is clear what we are talking about. So hopefully there won't be too much confusion. This will be defined as 1 if x was greater than 0 and 0 if x is less than 0. And at exactly x equal to 0, it is left open. We won't need it most of the time. But if there is a need for it, then we will average it. So there's a lot of ambiguity there, but we won't need to worry about that. If you were to draw this, imagine this to be x equal to 0, this is equal to 1, and this is equal to 0. So that's how it is. What is derivative of the Heaviside step function?
0 everywhere except at 0.
Except at 0. So it is 0 if x is not equal to 0. And if x was equal to 0, we don't know. But it seems like, since I have not defined at x equal to 0, I mean, if you look at this diagram, it seems like its slope is really large, so maybe it is infinite, but we don't know that. Technically speaking, we don't know. But remember that if you have something like this, you have to do this integral, right? What if I integrate the derivative of step function about any point, A and B, around x equal to 0, right? That was our idea of a delta function, right? And if this comes out to be 1, then maybe it is delta function, right? But what is this equal to? How would you evaluate this integral? d by dx of d by dx, or sorry, integral of d by dx? Like they cancel out, right? So they cancel out. And I just had to evaluate, so this is actually theta of x evaluated at x equal to b and x equal to a, right? So derivative and integral are anti to each other. So that's theta of b minus theta of a, which is equal to, if b was greater than 0 and a was less than 0, then this is equal to 1. If 0 was greater than A, greater than B. If both were less, it is 0. And it is 0 if A was AB is less than 0. And it is also 0 if A, comma B. So it satisfies the properties of a delta function. So we will say that step function, the derivative of step function is also a way to look at a delta function. But step function is useful. So let's think of a uniformly charged sphere of radius r and total charge q and charge q. Okay, so we would like to ask, what is the charge density for this?
Q over 4 pi RQ.
That's correct. Huh?
0 if it's outside.
0 if it is outside. So this is some. Let's say this is some constant c, like this, correct? Q over 4 by 3 pi r cubed. And then we have to write, it's not a delta function now, but it survives if it is a constant if r is less than radius r, and it is 0 if it is greater than radius r, right? But that can be captured using the step function. So you would say the step function is this is c times the step function. I have to have the step function says x is greater than 0. So that means r minus r is greater than, no, x is, it survives when x is greater than 0. So, survives, right? So I have to get this. So it is r minus r. So it's capital R minus r. Is that clear how I'm writing this? Okay, but what is C? I mean, Christian pointed out that it is charge q divided by 4 pi 3 pi r cube. But how do we know that? Just integrate this, right? So if we integrate over d cube r over charge density, we should get q, charge q. This is equal to dqr times, here we have c times step function, r minus r is equal to charge q. C comes out. This pretty much tells the integral that don't integrate beyond that point. If you want to specifically do it in spherical coordinates, this will be 0 to infinity r squared dr 0 to pi sine theta d theta and 0 to 2 pi d phi. Is that familiar? So what I've done is d cube r, the volume element in spherical coordinates is r squared sine theta d theta d phi dr, right? D theta d phi dr. Is that familiar? Is that a familiar thing? The volume element in spherical in rectangular coordinates, this is dx, dy, dz. So the volume element is this. So that's your volume element times c times theta of r minus r is equal to q. There is no phi in this, there is no theta in this, so these two integrals can be done. So this is just 2 pi. And if you were to do this integral, sine theta is cosine theta, go from 0 to pi, that just gives you 2. Right? Cosine theta, cosine of 0 is 1, cosine of pi is minus 1 when you subtract. That's 2, so that's a 4 pi in surface area, right? 4 pi. So this is 4 pi times c, and that is an integral 0 to infinity r squared dr times r minus r. This pretty much puts a cutoff in the integral limit. It says that beyond that point it is 0. This goes from 0 to r because beyond that point this is 0. I don't have to integrate beyond that, and I can forget that within that because it's 1. It is 1 from 0 to r, and it is 0 from r onwards. And this integral we know, right? So it is 4 pi times c. This is r cubed over 3. It's equal to q. And indeed, c is equal to q over the volume, 4 pi r cubed, 4 pi by 3 over r cubed. This is pretty much the way you would have integrated if you were to ask to calculate the volume of a sphere. This is what you would have done, except that you wouldn't have that c then. Right? So that's how you would have done the volume of a sphere. Here we equated that to the charge q, so we can calculate c. So what we will have in this whole course is that we will have a charge configuration. We should be able to identify the charge density and then accordingly proceed and work on with the Maxwell's equation. The first thing we will do is work with Gauss's law. So the Gauss's law will have charge density in it, and we will work with Gauss's law. That's what we will do next class. So you should be able to do the homework with whatever we have done now. And on Wednesday, And next Wednesday, on Wednesday, Friday, and next Wednesday, we will work on Gauss's law, and you'll have an exam on Friday. That's all. So review your Gauss's law before you come next time. That might help. Or an extra credit problem, right? What is Gauss's law? That's,
We have to use that extra credit.
yeah, what did I? Yeah, you have to show that. Substitute this in this, and show that actually you get Q.
Okay.
So substitute this inside that and show that it is charge free. So 2 extra credit problems. One is to show that for a line charge, if you do this integration, you indeed get this charge per unit length, and you should get the total charge. And the second is just to state what is Gauss's law. We talked about it in the first day of classes, but look into your introductory level physics course. Thank you.